Section 11.1 is basic notions, and that is basic notions of geometry. And we're going to start with some basic vocabulary. So, point. A point indicates a location or a place, not a size. And it's denoted by an uppercase letter. So we would identify it as capital A, not lowercase a. A line indicates length, but not width. Okay, so there's no thickness to a line. There's a couple of different ways that you can write line notation. So if you're given 2 points A and B, there's exactly or precisely one line through the 2 points. We name lines by either a lowercase letter, K, and it usually looks kind of scripted when you see it in print, italicized, okay? Or by using 2 points on the line. And it can be any 2 points on the line. Now, if we've already identified points A and B, we can use those. And on top of the A and the B, we write a line with arrows on the end. The arrows are crucial. If they don't have arrows, they have another notation. It means something different. So those arrows on the end matter. And here's why. These two right here will have the same notation, but they'll have a different bar on the top of our letters. A line segment is a piece of a line that contains 2 end points and all the points of the line in between those points. So visually, it looks something like this. Right? A line segment. We'll use the same letters A and B we used on the previous slide. And when we write this down, notationally, it has a straight bar on the top of it with no arrows on the ends. And that means line segment AB. The starting point has an ending point because there are no arrows.
Does it meet the points at the ends of the line?
It doesn't. In most places you won't see them drawn in. It wouldn't be wrong to do so, it's just not commonly used. Yeah. Probably more because it's faster without them, honestly. Yeah. Array is a subset of a line that has one end point, for example A, and contains point B and then extends to include all points on the line beyond B. So if we have here's point A and here's point B, then array would look something like this, where we draw an arrow beyond that and it would go on indefinitely, forever. Okay? And then when we write the notation, it matters that we write the end point that it starts at first, the end point that it goes through second, and then on the top of this we write that same arrow. Okay? So the part where you see the arrows match. So you have the arrow here going across for B, and the arrow is going beyond B over here. Okay? If you switch the notation, it would be a different ray. If you write down ray BA with the arrow, that would be this ray. It's a different ray. Okay? So the order matters, the arrow's direction matters. Colinear. Colinear are 3 or more points that are on the same line. You might say, why does it need to be 3 or more? Well, the reason it needs to be 3 or more is because there's always a line between 2 points, right? Every 2 points can be connected and have a line draw through them. That's not true for 3 points. So 3 or more points are special if they're all in a line, and we call them colinear. When A, B, and C are colinear, we say that B is between A and C if AB plus BC equals AC. Now, underneath there, I define what AB, BC, and AC are. So when you see those 2 letters and they don't have a bar on the top of them or a line on the top of them or a ray arrow on the top of them, it means distance. So if you see AB written and there's no bar on the top of it, it means it's a length, a distance between the points A and B. Okay? So this notation right here is a numerical value. It's a length. It's not actually a line segment or a ray or a line. So this statement right here is saying that when we add up the length between A and B plus the length between A and B and C, it will equal the length between A and C if they're collinear. So visually, let me just describe why that has to be true. So let's say that we have this line segment, AC, and we've said that we're trying to say that B is in between them. Well, whatever this length is, plus whatever this length is, should add up to the length of the whole thing, right? Yeah, I mean, like, that makes sense visually. So if they don't, what would have had to have happened? Well, it would have had to have done something like this. So here is length AB down here. Here is length BC right here. And when you add those two things together, I mean, you get the length if you were to travel along this path, if you will, but you don't get line segment AC's length, because actually that would be line segment AC, right? And that's not how triangles work. In fact, you know a relationship about right triangles in particular that shows that this doesn't work. But it doesn't work on any triangles ever. So you can't ever add up two side lengths of a triangle and get the third side length. Because if you could, then they would be collinear and you wouldn't have a triangle. Okay? So the reasoning kind of just goes around in circles a little bit. All right, we say that two lines are intersecting if they have exactly one point in common. So they cross, right? Like so. And if I'm drawing lines, I need to be careful, draw the arrows on the end, otherwise I have line segments actually. So those are lines. And we have concurrent lines are lines where there are three or more lines that intersect in the same point. We call that concurrent. So there's two diagrams below here. You can copy them onto your page if you would like. I don't think they're on there yet, are they? No, I didn't think so. All right, so on the left-hand side, are there any, the left-hand diagram, are there any concurrent lines? No. There are three lines, but they don't all intersect in the same point. So the three lines you see on the left-hand diagram are not concurrent. Are there any intersecting lines? Yeah, there's several intersecting sets, right? So an example of intersecting lines here would be what? So AB as a line with the arrow on the top, right? And what? BC. These would intersect. So those would be two intersecting lines in the first diagram. Do we have intersecting lines in the second diagram? Yeah, lots of intersecting lines, yeah? And we could write, I mean, still AB, or we don't have A and B, sorry. EF, tell me a line that EF intersects with. FG, and they intersect at point F, right? Yeah, so we could call it like that. Do we have any concurrent lines in that second diagram? We do. There's several places where we have three lines meeting at one point, and we can take any of the coordinates on this one because it happens sort of symmetrically. This particular point right here has three lines crossing at it, right? So we actually have a concurrent set of lines here. So what are the concurrent lines at the point where I've circled it in yellow? What are the lines that intersect there? EF. Make sure you're writing notation correctly. FG. And DF. Now, it's sort of in my nature to write them alphabetical like many of you just did. Do you have to? No. If you had written DF and I had written FD, would it be the same line? Yes, it would have. You don't have to worry about it because it extends in both directions. Rays didn't work that way, but lines do. Yes, Hannah?
On the intersect one, why was AC not an intersect?
It was, but it just doesn't intersect with the other two. So we just wrote down one pair.
Why not? Like, why does it not? Because, like, C wouldn't, like, why doesn't AC not intersect with BC? Like,
They do all intersect, but they don't intersect at the same point. Intersecting lines can only intersect at one particular point. So we were finding a pair of intersecting lines.
okay.
And I mean, we could have chosen any of them, actually, because they all do intersect with each other in the same diagram eventually, right? But they don't all three intersect at the same point. Yeah. Okay, any other questions about concurrent lines? All right, we're going to move into 3 dimensions. A plane indicates a surface, not a thickness. Now, when I think of plane, I often think of like the ceiling or the floor or a sheet of paper, but you have to understand that all of those objects we just described do have thickness and a plane wouldn't. You also have to understand that all those objects have boundaries, right? They stop eventually. So if I'm thinking of a sheet of paper, it has edges to it. But a plane would go on indefinitely along the same, sheet if it were to continue forever. So given 3 non-collinear points, there is exactly one plane that contains all 3 of the points. And I'll talk about that more in a second. We name planes by 3 points on the plane or by a Greek letter such as alpha, beta, or gamma. Our book tends to use, well, some of the diagrams it will use the Greek letters, but it tends more often in the text when it writes about it to identify that by 3 points. That's sort of the more common notation that we'll see in our book. So, I think I have one in the next picture. I do. I have a picture over here. All right, so we'll get to that in a second. Let me talk a little bit more about the plane idea. So if you identify any 3 points in this classroom, sort of the location they are in this classroom, there will be a plane cutting through them. So we'll do an easy one first. So we're going to use this wall over here. So if we use the top right-hand corner over here, well, it's your left-hand corner over here, there's a point where the ceiling, the wall, and the other wall meet, right? There's a point there in the corner. If I use that point, I use the point along the floor over there, underneath it, and the point along the back wall. How would you describe the plane that contains all 3 of those points? But a plane's not a triangle. It'd be the wall, but then extended in all the directions. It'd be the triangle, but then extended in all the directions, because it would have to extend up, down, left, and right. So that would be the plane that contains all 3 of those points. Obviously, it contains infinitely many more points than that, right? But it would contain those 3. Okay. So it's easy enough as long as we do it along one of the walls, the ceiling, or the floor. So let's do something a little more complicated. Let's do the same 2 points along the floor, okay? And then we'll do the corner over here of the classroom, top corner on the other side. It's not a wall that's going to connect all 3 of those, or a ceiling or a floor, right? It's not. But there is, if you will, going to be, and it would actually look a lot like, if you can imagine, I'll just pick it up, this, okay? These are your 2 corners down here from my classroom over here, and we have the top corner up here, and there would be a plane that would meet them cutting through like this if we were to vision it that way. And it doesn't matter which points we pick in the classroom or in any other spatial object we're working with, we're able to do that. Any 3 points. All right, coplanar points are points that are in the same plane. So if you give me 3 points, they're always coplanar because there's always a plane through every 3 points. Once you give me 4 points, they may or may not be. So again, if I use those 2 corner points along the bottom and the top right-hand one over here that we started with that was the wall, and then I add on that corner over there, those are not coplanar, right? Because the plane that contained these 3 points was the wall, the plane that contained the 2 on the bottom and the one over here was a surface that went straight through like this at the diagonal, right? And those 2 surfaces, those 2 planes were not the same. So there would not be a plane that contains all 4 of those particular points. Non-coplanar points are points that cannot lie or do not lie in the same plane. And then we have coplanar lines, and coplanar lines are lines that lie in the same plane. And of course that wouldn't always have to be true either. So if we did the line, if you will, that's along the bottom of our classroom over here, and we did the line that's along the top, those 2 are on the same wall and they're in that plane. But if we did the line that's along the bottom over here, and we did the line that's maybe connects this corner over down here to the top corner over there, those 2 lines would not lie in the same plane. One of them lie in the plane behind me on the wall, the other one lie in the plane over here on the wall. So those would be non-coplanar lines. All right, we will pick up with this picture next time, and I will see you next class period.